Following on from our discussion the last day about the basic notion of what is a distributed system and how it evolved, I want to talk today about the key attributes of a distributed system, the kind of things they really ought to have, and the kind of issues that they raise for us. First of all, we have this idea of resource sharing, that resources in a distributed system should be physically encapsulated with computers and should only be accessed from one another by some form of inter-process communication, i.e. some kind of method invocation. The manner in which the sharing is done and the physical distribution of end users determines the mechanisms that the system must apply and that are available. For effective sharing, each resource must be managed by a program that offers some form of a communication interface. For us, that is a programming interface, or what we call a service interface. That is to say, it is an interface that enumerates a set of methods with a full method signature describing concisely exactly what can be done in terms of method invocations with this given resource. A service, in the context of distributed systems, refers to an IP address port number combination in addition to an interface describing the methods that I just mentioned. The term server refers to a running process, basically something running at an IP address, usually on a given port. Clients or anybody's making, or any programs, either with a user or just a running service, making an invocation of a remote service. And we can have a multiplex situation where somebody is both a client and a service at the same time, depending on their interaction with another node on the network. A key aspect of distributed computing is the notion of heterogeneity. Basically, this means different types of networks, hardware, operating systems, programming languages, and application software. The issue of networks has long been sorted. It was sorted out in the 1990s when IP emerged as the de facto standard. Everybody accepted that, and the other standards slowly began to die. Computer hardware, on the other hand, is still an issue. We do have the differences between 32 and 64-bit computing, the distribution of software. We also have issues relating to the actual processor itself, whether or not it's big or little endian. This takes its notion from the Gulliver's Travels, where there was a civil war in Lilliput between people depending on whether or not you broke an egg from the big or the little side. In the case of computing, what it refers to is whether or not the most or the least significant digit of a binary bit vector is first on the left. In terms of operating systems, we're looking at the heterogeneity or difference between Windows operating systems, Linux, Unix, OS X, iOS, Android, even things like VMS. In terms of programming languages, low-level languages like assembler, C, C++, C#, Java, Python, and finally between application software themselves, Oracle relational database management systems, talking, for example, to a MySQL database server. What about some NoSQL database servers in there, like Neo4j, for example, MongoDB? And then we have the differences between things like web browsers, even, i.e. Chrome, Mozilla, different support for JavaScript and scripting capabilities, and different support for standards like HTML5, CSS. So these are major problems, and it's something we encounter the whole time in distributed systems, and a lot of the techniques we're going to be discussing are ways of circumventing these issues that arise from the heterogeneity of distributed systems. At the core of this, really, of our solution is going to be this idea of middleware, which is something that we find in Tier 2 of our N-tier client-server architecture. Middleware helps to solve the problems of heterogeneity by doing the following. It masks, effectively, differences by providing a layer, a software layer, an abstraction, a programming abstraction that hides basically those underlying issues: network, hardware, operating system, even programming languages, and to a much lesser extent, application software. The middleware is often called an application server. It's also called a middle tier application. And basically, it's the notion here is that we have some form of abstraction to decouple high-level components from their low-level details. This is known in object-oriented programming as the dependency inversion principle, and it's applied extensively in distributed computing. It also provides a uniform computation model for use by the programmers of distributed systems. And we saw this last week when we looked at core technology platforms like the J2EE framework on something like JBoss, WebSphere, ZK, .NET framework, things like Corba. We also looked at things like LAMP, for example, or maybe a JavaScript, Node.js type approach. And the key issue for us here is whether or not the type of middleware we're using is standards based or not. It can be an actual standard from a standards body like the W3C consortium, or it could be a de facto standard like most of the Microsoft software, or it could be more of a community based standard like most of the Java software, which is part of the JCP or the Java community process, acts as a body that to some extent anyway adjudicates on the types of capabilities that the J2EE application servers have, and they also collaborate on the formulation of standards or specifications. Another aspect is that of openness. Openness of the computer system in terms of its extension, and this is really another notion here of an object-oriented programming principle being applied in distributed computing. The principle here is the OCP, or the open-close principle. We're saying that the system can basically be extended easily and not so much modified as such. So it can be open or closed with respect to things like hardware extension. That is not what we're concerned with, but that would mean adding peripherals, for example. Okay, but software extensions, can I add more capabilities? I.e., can I create a single service by aggregating the cumulative capabilities of many distributed, heterogeneous, discrete services physically somewhere else. Openness is achieved by publishing, and again, it's a programmatic idea here, a key software interfaces, the service interfaces that are specifying the actual method signatures that you can use of the components of a system. The open systems are based on the provision of a uniform communication mechanism and the published interfaces for access to those shared resources, and these hopefully would be developed using open standards. For example, IDL in Corba, WSDL in web services, and to a lesser extent Java remote interfaces in J2E RMI. So open distributed systems can be constructed from heterogeneous hardware and software, possibly from different vendors. Openness implies some form of vendor, platform and language agnosticism. In other words, that we're not locked into a particular vendor, that we have the freedom to move. So the conformance of each component to a published standard must be carefully tested and verified if the system is to work correctly. And we're going to see that the openness can really be measured by the extent to which your middleware application server actually implements open standards. Security is going to be a major issue with any piece of software that's deployed in a networked environment. It's a major issue with any piece of software full stop, but becomes even more salient if it's on a network. So security from information resources has three basic components. We have the notion of confidentiality, integrity and availability. Confidentiality being obviously protection against unauthorized disclosure, integrity, protection against alteration, corruption, and availability, protection against access interference. We have a lot of technologies and theory that basically solve pretty much most of these problems, okay, in as much as is possible. However, in a distributed system, security is more like an onion, and I'm not referring here to Tor or the dark web, but it's not a bad example of it, that the actual security must be layered literally from the front, from the client, or all the way back, okay, to tier 3, and that includes all of the communication channels using HTTPS. It includes locking down the operating system and many other things. So even if a message is encrypted, knowledge of a recipient and sender can be used to do some profiling. You can also suffer a denial of service attack, which you can do absolutely nothing about. We have open ports, SQL injections, vulnerabilities in operating systems, people who haven't upgraded or applied patches, leaky firewalls. We also have things just sloppy user access and privileges on databases, fragmentation, But usually the biggest risk is Mary at the next desk or in the next office, who is either sloppy with their work or deliberately trying to taking stuff out of a secure environment and showing it to others, or just being sloppy with it, or perhaps even selling it. A major issue we will want to deal with is that of scalability. Scalability refers to the capability of a system to remain effective when there is a significant increase in the number of resources and the number of users. So increasing the loads expose limitations with centralized services, data structures, and algorithms. Look, if the application can scale from hundreds to thousands to tens of thousands of users, we would say that's pretty good. The performance does not degrade when the number of users goes up. So we have two ways of effectively doing this. We can have what is called vertical scalability, scale up, where I add additional resources to a single, almost monolithic computer architecture. In other words, I give it more RAM, give it a bigger disk, okay, and give it a faster processors, that kind of idea. That would work, but only to an extent. I'm probably going to have to combine that with the notion of horizontal scalability, or what we call scale out. Basically, have clones or replicas, or through replication or synchronization or some other form of collaboration that the load is distributed across more than one node on a network, and that allows the application to scale. Over and above that, we also have programmatic things that we can do here as well. It's the difference between synchronous computing and asynchronous computing. In other words, basic method invocations versus method queues, or message queues. So each component of a systems architecture contributes to scalability and has to be looked at, and it's something we need to concern ourselves with. Communication latencies, again, synchronous versus asynchronous, clustering, visualization, cloud architectures. We could have things like data replication, mirroring, and synchronization. These are different things. What about schemaless database management systems like the NoSQL variety? And we got the notion of Brewster's CAP theorem here about consistency, availability, and your capability of partitioning or distributing the components of a database. How can all these things be aggregated and leveraged to allow us to build a more scalable system? Another aspect of this, and it relates to scalability, okay, and openness, okay, is the notion of fault tolerance. Fault tolerance is simply a measure of how a system is able to manage when we have hardware or software faults. Okay, the actual faults or failures should always be partial in a distributed system. The system should continue to operate, albeit at a reduced level of operation. So the availability, the uptime of the system is closely related to scalability. Okay, how long is it in use, or rather, how long is it actually not in use over a period, say, of a year? We should be down to like just a few seconds if this is being done properly. This is not, and I should add, most of these key attributes like security are not handled just at a programming level. They're handled almost declaratively at an administration level. That includes the administration and management of the policies that underpin the middleware or the application server. So fault tolerance is provided by the failover support of the actual middleware itself. This handles it. It is not the type of thing that you have to actually program yourself. So fault tolerance relates to every component of an architecture, and thankfully we do have protocols that will manage these, from the actual networking side of things to the method invocations and retransmission of messages into message queues, database locks, rollbacks, that type of thing. It's difficult to determine if a remote host is actually is still working without constant polling. That in itself generates a large communication overhead, which could in itself lead to a performance degradation in the system. So these are things that we just have to consider, we'll deal with, but we're going to rely in the first instance on the middleware to solve them. Anytime you put any program on a network, concurrency immediately becomes an issue. We could have more than one person using it at any given time. In other words, our program, in order to be scalable, must support concurrent use. In order to support concurrent use, it must be multi-threaded. Now, the problem with multi-threading is it can get complex. It's the difference between having an application that is capable of handling tens or hundreds of users and an application that can handle hundreds of thousands of users. The good news is that middleware standards like J2EE allow us to basically build applications using the J2EE specification and not worry about the concurrency, not worry about the multi-threading. Again, we're going to let the middleware worry about these problems. It will also handle other things related to scalability, okay, and indeed, to a lesser extent, concurrency, like the activation and passivation of objects when they are or not being used. A really critical aspect, and we're going to be coming to this time after time after time throughout this module, is the notion of transparency. And this really is the concealment from the end user and the application programmer, that is ye, the software developers, of the different discrete components in the distributed system. In other words, the fact that the system itself is distributed should be hidden to the maximum possible extent. And there are different forms of this, which we're going to encounter time after time. First of all, we have the idea of access transparency. Local and remote resources are accessed using identical operations. We're going to see, folks, that the programming mechanisms for remote invocations is exactly the same as remote invocations. It's orthogonal. There are no special language, syntax, or grammars that we have to use in order to do this. Next, we have location transparency, that we're not bothered by the actual physical location of a particular application. We deal with it not by its actual location, but an IP address, which itself then is abstracted in the form of a domain name. Concurrency transparency is handled for us, hopefully, by the middleware. Replication transparency, again, handled typically at a data layer. Failure transparency and process migration transparency, all handled again by the middleware. And finally, performance and scalability. Those two forms of transparency are also handled by the middleware. That concludes, folks, our talk on the key attributes of distributed systems. In our next lecture, we're going to look at the ideas of method invocations and inter-process communications and the different models of those.